Alright, I'll be asking questions from individuals.
Wait, is your computer recording?
Yeah.
Oh, so you're gonna do a video of like screen?
Yeah.
Wow.
And I'll be calling out names at random. And when I call out two names, you'll have to come up with the answers. The other ones should try. So in case we are making a discussion, you should be able to contribute. All right? This Jet Price.
Yeah.
Are you Jet Price?
Garrett Price, yeah.
But now Jet Price.
Yeah, Chef Jet Price. Thank you very much. Yeah.
Jet Price. Okay. And
We turned off the light. You were angry kissing.
Brand Brown. What's up?
So
You two are gonna work together.
If you feel like you know the answer, give up. Yes.
D.
D. So it's your answer.
I mean, I haven't even read it. I can't see it.
It's been there all this time.
I mean, alright.
Here, do you want me to read it to you?
No.
Are you not able to read?
I don't have my glasses with me.
Okay, put the chair up here and then sit down.
I'll be very fun.
You got this.
If you turn off the lights, probably it might help.
Yeah, Bebo.
Oh yeah. Got a beef going. Yeah, we got Scout versus
Sorry, what?
We've done problems on ladders that inclined on the walls.
Just go D.
Yeah. D. D is right.
I'm gonna get D.
We did it.
You said D.
Any questions from anybody? Do you understand why it's D? Think of a ladder that is resting like this on a wall. If a ladder is resting, okay, that's a wall. If it is resting like this, there's a force from here pushing it this way. There's a friction holding it like this. There's a weight pulling it down here, and there's a normal force pushing it from the floor, right? Yeah. Now, you know the ladder is in equilibrium, which means the net force on the ladder should be zero in x direction and in y direction. So the two x forces, one is the push by the wall on the ladder this way, horizontally, and the friction from the floor in the opposite direction, they should be equal and opposite. That is the question. They're asking which of the following must be the same magnitude as the frictional force exerted on the ladder by the floor. The answer is the normal force exerted on the ladder by the wall.
Did they leave space for question?
You can always draw. If I'm you, I'll immediately draw and then verify that the thought process is correct. Alright, so some students want to calculate the work done by friction as an object with unknown mass moves along a straight line on a rough horizontal surface. The students have a force probe, a meter stick, and a stopwatch. Which of the following will allow the students to take measurements needed to calculate the work done by friction? So they have a force probe that will measure the force, a meter stick, they have a stopwatch. Which of the following will allow the students to take measurements needed to calculate the work done by friction? Kyle Philip. And there's Norris.
It's a force. It's work is done with time. picking B.
Yeah, that's what.
B.
No way, Jose. It's constant. It's constant velocity. Can't measure anything with that.
Now, any word in the problem should not be ignored. Okay, so as you read the problem, with an unknown mass moves with us along a straight line, on a horizontal surface, which is rough, which obviously means there's friction. The students have force probe, made a stick, and stopwatch, which is the following will allow the students to take the measurements to calculate the work done by friction. Now, work done, what's the formula?
Force times
Force times displacement. And the force should be the frictional force. So you want the frictional force measured and times displacement. So if you want to measure the frictional force, what option will we go?
C.
Anyone has a concrete answer? Yes. So pulling the block at an unknown constant acceleration with a force probe for a measured time.
No. C.
See, Kyle, what do you have?
Would it be C because the acceleration would guarantee you a constant acceleration, would that guarantee you a constant force in the distance for measuring displacement?
Now, when you apply a constant acceleration, are you measuring the frictional force?
I guess not.
So,
Huh? D. D is the answer.
I was originally
D is the answer. Why? Because when you pull the block at an unknown constant speed, as long as the speed is constant, what you know is the force probe is going to be reading a force which is exactly the frictional force. That is why it's going at a constant speed. So when you make something go at a constant speed, the force that you put on it is equal to the frictional force. Do you understand that?
Huh.
That is the concept. And of course you have the distance measured, so then you can have the force and displacement. So if I'm going to pull a chair with a force, and if the chair is sliding with a constant velocity, obviously I'm pulling with a force which is equal to the frictional force. Because if I pull with a greater force than the frictional force, it's going to accelerate. Get it?
Well, okay.
Next one. Read it. Hayes. Griffin. Oh, I said Hayes. Griffin.
That's Middleton.
Brandon Chow. Hayes and Brandon. Any answer? What is that? D. What about
I
Griffin?
think it's D2.
If that's the case, then that it is. It is D. Why?
Well, because I know the period's the same because like even on a pendulum, it doesn't matter how far you pull back, it's still going to be the same period. But so I assume that applies to the.
No, but the question is, the sphere is replaced with a new sphere.
Yeah, I
which
know that's
is
what I'm saying. So I think
mass.
I know
The mass
that
does
the same
not
thing
matter.
would probably apply with a new mass too.
Okay, mass does not matter, so time period is supposed to be the same. And maximum kinetic energy is supposed to be larger because the mass is now bigger and you're releasing from the same position. there's more potential energy involved, therefore there will be more kinetic energy involved. So that's right. And the maximum acceleration, again, acceleration does not depend on the mass. Acceleration is like g sine theta. You know, if you go back and look into the pendulum derivation, the acceleration of the pendulum is g sine theta. And therefore, the answer is D. Yeah, press again. Here we go. Planet X has twice the Earth's mass and 3 times the Earth's radius. The magnitude of the gravitational field near planet X's surface is most nearly what?
Okay, Bobby, that's not. That's not.
Take care of the computer, go drop it. Take care of that computer.
Oh, do you want me to touch
No,
it?
no, no.
No, he said
don't-
make sure you don't hit it.
don't-
Just for you to
Move.
Should I touch it?
I've been having that for many years and I've not a single scratch.
What's his name? Like, do you have the names for your car?
Yeah, you got 2.17.
My car's name was Joaquin.
Yeah.
Number plate is, does your number plate say that?
Yeah,
Alright.
this car actually is life on.
Oh, never mind.
The red one's the redhead stepchild.
Answers, Leo and Garrett.
And go with the solid C.
So let's see. You know, you can take G of Earth to be 10. So on the basis of that, Earth's G on Earth is taken as 10 for multiple choice questions. You don't have to take it as 9.8, just take it as 10.
That's
Now this problem can be done logically. You can also do it algebraically and prove it. I'll show you both. Is it A?
It's twice the Earth's mass.
It is A. It is A. The equation is G is equal to Gm over x r squared. Check back into your notes. You'll see that equation. G is equal to Gm over r. So if you're going to write G is equal to Gm over r squared, that is for GE, and that is ME, and that is RE. Now write a similar equation for planet X. For X, it is Gx is equal to G mx over, okay, what is mx? 2 times me. And what is RE? The new planets? It is 3 times RE square. What is 3 times RE square? 9RE square. Now, after you write these two equations, just divide it. So when you divide it, you get GE over GX is equal to this term divided by this thing, which is equal to GME over RE square divided by
9RE squared.
9RE square over G2ME. And you can now cancel off all those things. And then finally you end up getting GE over GX is equal to 9 over 2. So what is GX? It'll be 2 GE over 9. And GE is 10. So 2 times 10 over 9, which is close to 2. You get it? This is showing it algebraically. Now, if you don't want to show it algebraically, just do it in the head itself. Stare at this equation for some time, you'll get it. Look at this. GE is GME over RE squared. Keep an eye on this. G is capital E is a constant, right? Now they say the planet X is twice as massive. So what will happen if the mass is doubled here? What will happen to the acceleration of the gravity? It'll be doubled. So instead of 10 on the Earth, it'll be 20. Now RE is radius. They said the planet's radius is 3 times bigger, which means it is going to be 9 times smaller than 20. So what is 20 divided by 9? And you get the answer. You get it? 20 divided by 9. Yes.
Why do we multiply
Because I flipped the other term. See?
by 9?
Oh, 3RE the whole square is 9RE squared. 3RE the whole square is 9RE. Like if you triple the distance square is going to be 9 times 9. Take some examples. Let's say distance is 5 meters. Okay? What is the square of that? 25. Now, triple the initial distance from 5 to 15. What is 15 square? 15 square. 225. So 225 is how many times bigger than 25? 9 times bigger. Oh, take some simple numbers. 10. 10 square is 100. 30 square is 900. So when you square, it's simple as this. 3RE the whole square. So 3 gets squared and RE gets squared. Algebraically.
Yes, sir.
Alright? Alright, the next question. Read it. Graham Brown. Harrison Snyder. What's the answer? Now again, as before, I said it before, don't ignore any word from the problem because a word is put into the problem for a reason. Don't read over it and not use it. Every word has to be used.
B, 14.
C.
What he says B.
Well, I kind of said it because I knew there was friction. I feel like friction would take up some of the force, so that's why I was gonna go for something less than like 24.
Trying to go for a little guess.
A little bit.
Little
But I
bit
was
of
going,
guess. That's an educated guess. What he's done just now is an educated guess, which looks like the answer is B. So how do you do it properly? It says the 5 kilogram block is moving. It's made to move across a rough surface, which means there's friction. The magnitude of the force is initially 5 Newton, and the block moves at a constant velocity. What does that imply?
No acceleration.
Which means what? Friction is 5 newtons. Because you're pulling with 5 newtons and it is not accelerating. That means friction is 5. That's what is implied from there. You understand? So you understand friction is 5. Now, the force is increased to 12 newtons. So obviously it's going to accelerate because there's a net force. What's the net force? 7. So the net force is 7 and you're moving at a displacement of 2 meters. So how much work is being done? It is 7 times 2, 14 joules. Which means the kinetic energy has to gain the same amount. The work done is equal to the kinetic energy gain. So that's exactly what it is. So now what Grant did was this. He said 12 times 2 is 24 joules, but definitely there is friction involved. Therefore it can't be 24, it has to be less than 24. And therefore he just went for a guess between these two, which is 14. Right?
Yes.
Yes. That's why I said it's an educated guess. But it's better to always tackle the questions right straight away.
Don't.
Keynes building.
Carson, Trevor. Carson, Trevor. Answer B. Let's look for Carson.
Oh no, D.
Huh?
D.
D. Why do you say so?
I don't think it would vibrate because there's no medium for it to go through.
That is good thinking. The answer is D.
Person probably heard me say that.
Oh yeah, I heard something.
This is now. Therefore, one thing you have to understand is this: don't get when you look at a problem, don't let the problem perplex you. You know, like when you see so much, and suddenly you may think that the problem is a big one, but read it carefully, and you can easily understand this whole thing is based on just 2 words. When you say string 1 is plucked, so it vibrates in the pattern shown. Very soon after string 1 is plucked, string 2, which is a short distance away, vibrates. What is that?
Not connected.
What is the concept there?
Sound.
Huh? Resonance. Remember I put a tuning fork over there and I put a tuning fork over there and I hit this and that started vibrating? That's resonance. That's exactly the concept here. It's one guitar string and the other one matches perfectly and so it starts vibrating. And that is purely resonance. And then they say the guitars are then placed in a sealed chamber, like in a sealed room, and then air is pumped out of one chamber, of the chamber. Now, air being pumped out simply means there's nothing there, it's just vacuum. String 1 is plucked and it vibrates. String 2, does the string 2 vibrate in the pattern? That's the question. So, now this time we are saying It's not going to vibrate because there is no medium to take the energy. Mechanical waves needs a medium. Without a medium, nothing is going to go. So if I talk in vacuum, sound is not going to go out. My vocal cords may vibrate, but it won't generate the sound. Okay, vibration causes sound, but it needs a medium to pass the energy. So if you keep a loudspeaker in vacuum, it's not going to produce anything. Okay. We don't have a proper gadget, but there is an experiment that demonstrates this. It is a bell jar, and it's connected to a vacuum pump. So initially the bell jar is kept over something, and there is an electrical bell. So the electrical bell is operated, and the bell will ring. So you can see the bell kind of hitting like that, and you can see the bell vibrating, and you can hear the bell pretty well. And as the bell is ringing, you connect it to the vacuum pump, and as the pump is turned on, it evacuates that glass chamber, and the bell will be seen to be hitting like this, but you won't hear the bell. Sound cannot pass through. So yes, so don't worry about the question size. Sometimes when the question size is big, the answers are faster. You can actually get to the answers faster. Yeah, look at this picture first. Obviously it is resonance in tubes. And then read the question. I'll expose you. Griffin.
Griffin's just a lucky man, is it?
You should go for lotteries. You can win a lottery.
I want to be in third grade one time.
Oh, yeah.
That's great.
Is that going to be on the whole?
Did you win it? Or did you?
You go back down to the options. B.
Jim, I could agree with that. You agree with number
What's that answer?
C.
C.
Why would it be
If anyone knows the answer, sure. Yes, Nick.
Sorry.
D.
D. Okay, let me give you some backing on this, since you're confused on this. How many wavelengths do you see from here to here?
One.
Four.
Four is one.
A fourth.
Nuts.
This is an antinode, and that's a node, so it's 1/4 of a wavelength.
Oh yeah.
From D to
Carson and Sam, student affairs.
So there goes our answer. Talking about the same thing, and don't get too
All right. So this is 1/4 of a wavelength. How many 1/4s are here? 7 1/4s are there. So which one has a bigger wavelength? This one or this one has a bigger wavelength? So Y has a bigger wavelength. Obviously X has a smaller wavelength. Right? Now tell me the answer. The answer is A. The answer is A because lambda of X is 1/7 of lambda of Y, because very clearly the same length accommodates 7 of these. So this one is 7 times smaller. compared to this. Make sense?
What do we get down again?
Oh, you go down to the
Oh yeah, that makes sense.
Make sense now? Here is another question. This is a disc rotating on a frictionless axle, and a piece of clay is moving towards it. So that's a clay that's moving towards it with the speed of v/2, and the disc is spinning with the speed v. The outside edge of the disc is moving at a linear speed of v, and the clay is moving at a speed of v/2. The clay sticks to the outside edge of the disc. The clay sticks here. How does the angular momentum of the disc, of the system, after the clay sticks compare to the angular momentum of the system before the clay sticks? And what is an explanation for the comparison? So what is going to happen to the angular momentum of the system is the question. Oh, this one is Grand Brown. And Andrew Lennon.
I should have taken
So you are comparing the angular momentum of the system after the clay sticks to the angular momentum of the clay before the clay sticks. Andrew, have any answer? What's your, anyone has a feeling that you know the answer? Yes, Carl? G is it's less than because the angular momentum of the clay opposes that of the disc.
I said sorry.
What about Hunter? D also? It's the angular momentum. You know what is the formula for angular momentum? What is the angular momentum formula?
R omega.
R omega. Not angular velocity, angular momentum. Omega is angular velocity. What is angular momentum? What is linear momentum?
Mass times.
Mass times velocity. What is angular momentum? Inertia. I times omega. You got to go back and read all those things. I omega is the angular momentum. Brandon, you have an answer?
I think it's B.
B, it is greater because the rotating mass increases, which increases rotational inertia. B is true. B is B. The last part of B says which increases rotational inertia. That part is true. The last part of B is true. Let's see other options. Hunter, yeah, already answered. Andrew again.
My Andrew guesses.
Yeah.
I know it.
I mean, A is the only one that we haven't said.
That is the answer.
So.
That is the answer. A is the answer.
Is it because of conservation of momentum?
Exactly.
Oh no.
Conservation of angular momentum. They're talking about a system. They're not talking about one object. They're talking about the whole thing. So momentum is conserved because there's nothing else is acting on it. So just the clay gets stuck to the disc. So what happened to the disc? It will have a larger moment of inertia, but it is slowing down. So the total I omega should stay fixed.
I don't want to key in.
You understand that part?
He had 6 for 6.
Agree for some.
We asked how many hands.
That's attractive.
Now this can be a little on the tougher side when you want.
We're on a mama, let's see.
Read it first. A disk of known radius and rotational inertia can rotate without friction in a horizontal plane around its fixed central axis. The disk has a cord of negligible mass wrapped around its edge. So you can understand the cord is like wound around the edge of the disk. The disk is initially at rest and the cord can be pulled to make the disk rotate. Which of the following procedures would would best determine the relationship between applied torque and the resulting change in angular momentum of the disk? So you're looking at torque and angular momentum. What experimental procedure will best determine the relationship between applied torque and the resulting change in angular momentum? And they said it's got a known radius and a known rotational inertia, so those are not going to change. The radius of the disk is not going to change, so inertia is not going to change.
I know it.
Let me give winnings. Patrick,
Yeah.
Hughes,
Yeah.
Sam, question number 21. Very good.
But no, not going over there.
See?
Make no names.
I'm trying not to get in Carson's way.
Any answers?
C.
AM,
We're gonna put an all in on C.
going with D.
Okay.
Jackson,
Say C. It's got to be C.
It's not D.
I didn't say it's not D.
It's not.
I was just asking for answers.
Oh, I thought.
It is D.
I thought he couldn't hear the answer and he was like, oh, that's so wrong. He's gonna pick it first.
That's what
Now, the concept that is to be thought about is this. See, when a force is applied, for a certain time, you have change of momentum, right? Linear momentum. Correct? Is this okay? Now, in terms of angular momentum, instead of force, we have torque times time should be equal to I omega. Now, they said the radius is fixed. That means the torque, torque is force times perpendicular distance. So basically force times radius. So torque can be measured by the forces. And they said I is a constant, so you can actually measure those two at a fixed timing. So that is exactly the option there. The option here says use 5 different forces of different magnitudes, but keep the time the same. And that will be helping you to kind of plot a graph to find the angular velocity. Because you're keeping I constant, R constant, everything is kept constant, so D is the answer. $22. Liam Gray. James. So about Liam?
B.
C. F over 3. Yes.
I go with C.
F over 4. What formula are you using?
Q1 times Q2 over D squared.
Q1 times Q2 divided by
D
D squared. Did you use it properly?
No. Just
You can pretty much do it like how we did the gravity thing. You can almost do the same way.
if it's just 6 over 1 is F. So F is 6. And then the second one is
Exactly, yeah, that way.
4.
So if you do F, initial force is going to be, the product is going to be 6 over 1 square, which is 1. So 6.
F
And when you change the object,
is D.
what's going to happen? What will be the new force? Is the question.
It's 4 divided by 4. Wait. Yeah. It's 1, so it's 1 6.
You have to write it down, then only you'll get an idea. Unless you write it down, you won't get it. See, the first time the force F is equal to, see, I'm not going to write the micro and all that because micro is going to be always there. So I'm not putting the micros, I'm only putting the numbers 2 and 3. So 2 times 3 is 6 on the top. I'm not even writing the K. You don't even write the K. Or if you only can write the K, no problem. Put the K there. Divided by 1 square, so that's it. This is the force initial. And what is the force final? It's going to be, the K is there. What are the two charges? 2 and 2, that's 4. And what is the distance square? 4. So you have this. So F2 is just K and F1 is 6K. So what is the new force in terms of the old force?
The new force is 1 6.
1/6. That's the answer.
Ding dong.
I understand.
Yeah, just make sure that you always like think in terms of those equations. Now these things are not. You can see it is quantitative, but at the same time it is something that you can do by proportions. So you have to make sure that you look in the right direction. Here is a boulder. The force is applied to the left, and there is no acceleration. What do you mean by that?
Friction.
There is a constant friction that is pulling it, which is exactly the same, right? That's what this means. Now here it says this tractor is now pulling this wagon, and the force is applied, and there is an acceleration.
That means the rock weighs less.
Now he's pulling the truck.
Now it is pulling the truck with a force F, but the acceleration is to the right.
Oh, that's K.
Answer those questions now. Travis, Nicholas, wait.
I've only read the answer A so far, but that looks pretty right.
Nick Stubble.
Yeah, I think it's A.
It's C.
The question is asking which of the following is a true statement about the object and the relative magnitude of the force exerted by the object on the tractor. I'll go by vote. How many of you think A is right?
I think it's C.
How many of you think A is right? No one thinks. B. Okay, raise your hand if you feel like that. If B is the answer. C. D. Why D? Yeah.
Because the
Newton's third law.
Newton's third law. Simple. That's it. There's nothing here in this. See? All this problem winds to only one concept, which is Newton's third law.
What's that?
It says it in the question. It says
See, whatever be the force on the rope, that is going to be the exact force this way. So the boulder is going to pull the tractor with the same force. The wagon is going to pull the same force. The truck is going to pull with the same force. So that's Newton's third law. Straightforward. Now let me give you some foundation on this. Here's a star and a planet. I need to give you some information first before you go to the problem. The planet is spinning around like this. Now this is spinning in an elliptical orbit, which is what normally happens. Just as the electrons spin around the nucleus, same way. They are all spinning in elliptical orbit, not circular orbit. So this planet is going around like this. So sometimes it gets close to the star, sometimes it's going further away from the star. That's exactly how it spins. Now, when it comes closer to the star, it is losing its potential energy a bit and gaining kinetic energy, which means it will actually speed up here. And it will slow down here at this point. You can answer it also by using angular momentum conservation. What's angular momentum conservation? When this planet is spinning here, it is spinning through a smaller radius, which means less inertia. So the omega has to be big. And when it's spinning here, the radius is big, which means it's got a bigger inertia, and therefore the omega has to be smaller. So that is why the planets actually move like this. They come closer and they go faster here, and then they slow down here. And then when they come here, they go fast. And then when they come here, they go fast. Have you seen those animations like that? Electron spinning. It won't be spinning constant speed. You go faster at one spot, which is here. Now the other concept that you need to know is this planet has two kinds of energies. One is potential and gravitational potential energy and kinetic energy, both. Now gravitational potential energy, can you tell me what is the maximum gravitational potential energy that any object can have? What is the maximum gravitational potential energy that any object can ever have? Huh? What is the maximum gravitational potential energy that any object can have? In other words, this cup is here. If I take it from here to a higher altitude, is it gaining energy?
Yeah.
Yes. If I keep taking it up, it's going to gain. Finally, what is the highest gravitational potential energy you can give to it? Zero.
Ding dong.
Zero. Zero is the energy because once you take it to infinity, it doesn't have any potential energy. Which implies what? Which implies the potential energy that it has right now is negative. We all have negative potential energy right now, like 10 power 9 joules, but it's negative. So gravitational potential energy can never be positive. It's always negative. Understand this?
Yeah.
Okay. What about elastic potential energy? Elastic potential energy is the other way around. If a spring is like free, it is relaxed, what's the elastic potential energy? Zero. That's the lowest that you can have. Now if you pull the spring, are you doing work?
Yeah.
So it is gaining potential energy. If you push the spring, are you doing work again? So it's gaining energy. So whether the spring is pushed or pulled, you're giving it potential energy positive. A spring can only have a positive potential energy and the lowest it can have is zero. Now, that being said, this planet now has a negative potential energy, which is a big amount of negative potential energy, and it has kinetic energy too. The sum of the kinetic and potential energies adds up to a negative quantity. Okay? It will be a negative quantity if you add up those things. Now, keeping that in mind, let's read this. The planet is in elliptical orbit. Which of the following best represents the mechanical energy of the planet alone? The mechanical energy of the planet alone and the mechanical energy of the star-planet system as a function of time for one complete orbit. That question takes a whole page.
C.
The answer is expected from Philip. Jonathan, stop. Yeah, you can. Only if you have eye issues, I believe.
C.
Answer is C. C is correct. Because you can see C, that as it comes closer, it's picking up the energy and then goes down again back to normal. And here you can see the total energy star planet system is negative. All of them are negative. But it's a constant. Why? Because of energy conservation. Energy conservation. That's the reason why this is like this. Now, this is the next question. A force probe, a force sensor. A force sensor is a gadget that senses a force exerted on it, obviously. and a cart is moving towards it, hitting it and bouncing back. So a cart of known mass moves with a known speed along a level frictionless track as shown. The cart hits the force sensor and rebounds. The force sensor measures the force exerted on the cart as a function of time and as a function of position. So you have force time graph, force position graph. Position also implies displacement. The results will be graphed on the axis shown. Which of the two graphs can be used to determine the cart's speed after it rebounds? You already know the speed with which it's coming and hitting. You want to know the speed after it rebounds. So which graph will help you to determine the final speed after rebounding? That's the question. Sam once again. Travis.
I think it's G.
Say it again.
D.
D.
Yeah.
Neither graph is sufficient. Both. Let's see.
What is it? Can you scroll up? That's audience. I'd say the one axis, what the y-axis goes under force.
Force, time, force, position.
A.
Let me just give you a little briefing on this. Alright, force time graph. What can you find from the force time graph? If you're given a force time graph, what can you find? What information can you gather from a force time graph? Like in terms of either the slope or the area or whatever. Impulse. Impulse. And what is impulse? Change in momentum. So if you can find the force time graph, so if you have a graph, in fact the graph will be shaped like this. Force time graph will be like this. Now the area gives you the impulse, which is change in momentum. Will that help you to find the final speed?
Yes.
Change in momentum is known, initial speed is known. So can you find the final speed? Yes. What about this graph? This is a force position graph. Now the force position graph is going to be, the position is going to be like negative and positive. So it's going to be like this. What is the area of the force position graph? Force displacement graph. Huh? Work. FD. So think of those equations. FD. So it will tell you how much is the net work done. So if you know the initial speed and you know the net work done, can you find the final speed?
Yep.
Yep.
Let's see.
So C is the answer. Both graphs are fine. You can use both graphs to get to the answer. Oh, all right. We'll do the next.